All right, we're recording. This is I think it's the third lecture, but we're already on lecture 4, really, which is, this one I did not translate, because it was, I don't know, I forget why, but because I thought there's a lot of diagrams, I thought I can explain it. So now we're talking about a different kind of diagrams. We finished the DFDs last time, and today we're going to talk about use cases, which I think are the most relevant thing, even though they're really the simplest, but they're the most relevant because they're showing you how you use the system. Use cases. It's funny, he made a mistake. It should be use cases, no S there. But it's how you use the system. Cases in which you use the system. We're also going to do an activity diagram or different, yeah. So let's see. So it's part of the UML as opposed to DFD, which is not part of the UML. So now we're doing the rest of the diagrams that we're going to do are actually part of UML. And UML was started by these 3 characters. And the interesting thing is they each had their own methods of how to do object-oriented programming diagrams, class diagrams and other ones. And they each had their own ways, some with circles, some with squares, some with the arrows pointing this way, some with arrows pointing the other way. And they realized that this was silly, that everybody has different ways of doing things. So because you learn to read one and then you don't understand the other one. So they decided to instead of competing with each other, to work together, and they made this unified. That's why it's called unified modeling language. It's unified because it's not anything like it's just because they unified their different methods. It's the unification of these 3 guys' theories about how to do it. So fine. So these 3 guys are called the Three Amigos, and there was version UML 1.0, anyway, in the 90s, etc., etc. The OMG is a nonprofit organization started by HP, IBM, Microsoft, Oracle, Rational Software. Well, now I think Rational has been bought by Oracle. Anyway, that promotes the standardization of object-oriented technology by using guidelines and specifications such as UML. Okay, so by the way, I have a friend who went to Machon Lev, and he's about 20 years ago, and I'm going to have him come and speak to us actually about how they design software in his company. And they actually do use some of these tools. So lest you think that this is completely pointless, it actually is in big companies it's used. In other words, he was complaining to me, it takes them 6 months of planning before they can even start programming. Again, it's a bigger company, and they want everybody to know what they're doing. UML is a graphical language. It is capable of describing all the parts, all the life cycle of a project. It has diagrams. You can model and detail and describe the products of the software, whatever, the software. So here's a nice diagram. We actually saw this before, but it shows you that it's sort of using UML to describe UML. It's sort of funny diagram, right? We're using UML class diagram to describe the types of diagrams that there are in UML. And here's class diagram, which is a kind of, or it inherits from, so it's a kind of structured program, which is a kind of diagram. And there's also here sequence diagram, communication diagram, which are all interactive. There's also activity diagram we're going to do, use case diagram we're going to do. So these are all types of diagrams. Fine. So here, this is just a list of some of the things that are in UML. So here are some that we're not going to use, but you may come across them in the future. State charts. You're going to see state charts. Actually, you already saw state charts, I think, in if you did you guys learn our computer architecture with me?
No.
No,
yeah, we did, but also we
Yeah.
saw state charts in digital systems.
Digital systems, but also in computer architecture, you did state charts, right? Anyway.
Yeah, I think so.
State
Yeah.
charts in advanced object orienting.
Okay, so there you go. At the end of right, so there you go. Who taught you computer architecture? Avi?
Yeah, Triceman.
Yeah.
But we didn't learn state charts in
Yeah, he doesn't do them, I don't think. All right, so now we're up to use cases. Now, use cases are, like I said, something that I think is useful. In other words, I think it's particularly more useful than other things. So we said that the defining of the drishot is a choseh, is a contract between the client who's buying it and the leaders of the project that are making this system. And the use cases help describe what the drishot are, what the requirements are, because it's going to tell me what the system must do. Every requirement is modeled by a use case. It's a description of a group of interactions between the user and the system. How the user, or as I say, how the user uses the system. It captures the dynamic behavior. You see, what's it called? A class diagram just shows you what classes use what. It doesn't show you how the system works at all. It doesn't show you what you can do with the system. It just shows you this class as a pointer to that class. Thanks a lot. But what can I do with the system? Doesn't give you, so the use case does. The way in which a user will use the system. That's what it is. So let's look at one example. This is a use case. You can see that it is very simple. A patient uses the system to do something called make an appointment with the doctor. And we call the patient an actor. He is an actor. He acts in the system. The name of this use case would be make an appointment. Okay. We always use this stick figure to represent the actor. Even if it's an external system, we use a person symbol. Now we can have a more complicated one, because we're going to show all the people that use the system. We don't just show one person, we show them all. So here's make an appointment. You see that make an appointment is used by the scheduler and by the patient. Cancel appointment also. Request medication, that you have to have the doctor involved in. And pay the bill, you have to have the clerk involved with. Now the scheduler and the clerk could be the same person in your company. There could be different roles. In fact, all three could be the same person. The doctor could, but he might have to log in as a scheduler, or it doesn't matter. That's a scheduling activity, and it could be divided into a separate user, so it should be. Okay. In other words, we don't have to imagine, we can imagine a doctor who doesn't do that. So therefore we can make it separate. So we use an ellipse, as you saw. An ellipse is what some people call an oval shape. Although my father told me that an oval, this comes from the word ovum, which is Latin for egg. And an oval is actually egg-shaped, which means it's fatter at one side than pointier at the other. That would be true oval, says my father. But you can actually, I looked it up recently, and actually you can call an oval. You can call it also you can call an ellipse an oval. It's allowed. Anyway, we call this line that connects the user to the case as an association. So we have three things. We have the association, the actor, and the use case itself, or the case itself. The name of the use case is inside that ellipse. So let's keep going. So give names that are meaningful, that describe properly the actors and the use case. You can add notes if you want. Like you can add a little paper or something here. A little paper symbol and put it there. Here's another example. So we have the clerk, and on the right we have the client and the well, the clerk at the, I don't know what it, I don't know what this is, Dayal Rechev. But we have the client. He can either take a car, he can either order a car, take a car, or return a car. I don't know why it says Dayal Rechev.
Dayal is a clerk.
Dayal is Dayelet is a stewardess, and a Dayal is a steward. I don't know what a car steward is. Maybe
Nowadays, it's progressively accepted to call them flight attendants.
flight attendants. Yes,
Yeah.
you can call them that. But you can also call them a steward.
They don't
Flight
like that.
No, they don't like that. Flight attendant.
Differentiate between male and female.
So what about like mother, father? Can you call that just parents now?
Yeah, that's a good point. We should start doing that.
You should start just call them parent. This is my parent.
Primary caretaker. I am in need of assistance. Sorry.
Yeah, it could be not a parent, right? It could be adoptive parent. It should be just legal guardian. This is my legal guardian. I'm against, I believe that all this correct speech is what brought us a counter reaction of overly conservative idiots. And therefore we should keep to normal speech. They're perfectly good words. Like, stewardess.
Like stewardess.
Yes. And if the man doesn't like being called a stewardess, that's his problem. He should learn to have thicker skin. If I want to call the men and the women stewardesses, my prerogative. I can call them whatever I want. They don't have to like it. Great. If I said, "Hey, dog," I guess they wouldn't react so much. They would be insulted. But that's because that's intended to be insulting. But if I just call him a stewardess because I think that he's a stewardess,
I think you'll find that the overly conservative people will get offended if you call them idiots, even though they claim not to be offended by things.
Well, that's the thing. There's a difference between intending to call them a name and not intending to call them a name. In other words, if I call a man who thinks he's a woman a man, I'm not trying to insult him. Even if he corrects me and says I'm a man, well, it's difficult for me to remember that, so I'm going to keep calling you a man because to me you look like a man, even though he thinks he's a woman. So I don't think that's intending. Whereas if I call him a dog-faced buffoon, that would be more offensive. I think there's a difference between using normal language and using offensive language. If I could be offended by being called something, that just because I'm personally offended doesn't make it offensive. I'm offended by being called, a Jew boy, but that doesn't mean Jew boy is offensive. Oh, that was a bad example. Anyway, Magdir Gvulot. So now we're just saying what are the advantages of the use cases. It defines limits. It tells it can be used throughout the entire development process, because you can always look back at it and say, oh yeah, that's what I'm supposed to do. It defines needs, how to satisfy those needs, what the system should do. Short, it's also very simple. The client can understand it and I can understand it. That simplicity is good because I don't know who the client is. He could be a conservative idiot or a liberal idiot or a, indeterminate idiot. Could be a dog-faced idiot. And this is a simple diagram that anybody, even a dog-faced idiot, could understand. So that's good because we want to be clear. We don't want him to say, well, I misunderstood. I thought it meant something else. Okay. It also helps us know how to do our tests afterward, our code tests. I hope I'm not offending anybody who likes dog faces. Anyway, so here's the famous example that we always use. The money, what is it called? In English, in Hebrew, we call it kaspomat, teller, automatic teller, or teller S. So you can go to this automatic teller S, and what you do is you enter your code, your card, then you put your PIN, then you select how much money you want, then you confirm how much money you want, then you get your receipt, and then you take out your card, something like that. Would you say that is the right use case, or would you say the right use case is just withdraw money? It's a hard one.
B.
B. Yes, I would say B too. This is the process inside of B, but this is the use case. A case of one way to use a teller machine is to withdraw money. Another way is to vandalize it. Another way is to, take out the receipts for the end of the day, and refill it. There's other ways to use it or check your. Those two are bad examples. Better example would be like check your balance. I'm not withdrawing money. I'm just checking my balance. That would be another use case of the system. Withdraw money is one. Check my balance is another. Maybe send money to some yeshiva or tzedakah or something. Maybe or to another bank account that I want to. So B is the correct answer because it describes how we use the system. But obviously, it's not going to be enough to just draw a stick figure and a circle and say we're done. I mean, it would be nice. That is kind of what we're saying you should do. But we also have documentation. So we have the short and the full documentation. We'll see how to do the full. This is the full and the short. You see here, the full is like here, and this is the short. Now, the use case is like this. This is the description. This is how for every use case that you make, you need to draw this box and have in it the name of the use case, a brief description of the use case. You need to write this column and this column. And then your preconditions, a description of the condition that must be satisfied before the use case is invoked. There are different ways of explaining what this means. One way is to say it means like, what will have happened, like a postcondition is like, what will have happened at the end of the case to indicate that I am at the end of the case. In other words, the end of the use case might be that I've got a receipt for the money that I was given at the Kaspomat. By the way, my father used to say at the Kaspomat, you shouldn't count your money. It's kind of like the gambler. When you're sitting at the table, Don't count your money when you're sitting at a table. He said, don't count your money at the Casper mat. Why? Because if it's wrong, what are you going to do? You're done. You know, the door closed, and the next client's coming. You have nothing to do if it's wrong. So just put it in your pocket. You're stuck if it's wrong. So basically, if it just gives you a receipt and no money, that's it. You just got the receipt. But why do I say that the post condition is that you have your money? But actually, the post condition is more than that you have your money. It's also that your account balance has lowered by the amount you took out, right? That's a post condition. That it should have happened. If the case worked correctly, the money is in your hand, the receipt is in your hand, and the balance has been lowered. If it wasn't a withdrawal money, but it was a deposit money, then the balance would be raised. If it was a transfer money, then the balance would be lowered and some other account balance would be raised. Those are the post conditions. So what's the precondition? So one way of saying the precondition is that, it gets a little bit absurd at a certain point. One way is that you have money in your account. Or another thing you could say is that you have an account. Another is you're a human being. Another is there's electricity on the system. That's one, right? But those are all kind of, someone get a little bit crazy. Obviously that you can assume that there's electricity in the system. That's not, and you can assume, and to withdraw money, you must have money, presumably. Well, maybe not. Maybe you don't. Maybe you can go to debt. Maybe that's not a precondition. Maybe the precondition, and that you have access to the system also doesn't seem like a precondition. So what is a precondition? Condition that must be satisfied before the use case is invoked. I don't think you can say logging that he successfully logged into the system is a precondition, because you should say, I would say like this, a precondition here is that he has an account. You can't withdraw money if you don't have an account. Logging into the system is a bit dumb, because that's obvious that you can't do any use case you can't do if you're not logged in. And you can say, but having an account also maybe, but maybe not. Maybe there's certain things you could do without an account. Maybe you have a guest account. Maybe there are guest behaviors that you can do. But withdrawing money, you have to have an account. I don't know. It's a complicated thing. There's a whole nother way of thinking about preconditions and postconditions, which is where in the system should you have been in order to execute this command? And postconditions would be, where does the system leave you off? Like when you finish withdrawing money, it could be that you now are asked, do you want to do anything further? Or it could just slam the door shut and say, next client, please. So those would be two different, they're similar in the end if you think about it. They're similar in the end because a postcondition says, what's happened now? Well, the money has gone down, but also you're logged out. So they kind of relate. They're kind of the same thing. Are you guys there? I don't see any human beings.
I'm here.
Daniel Klein is appearing and not appearing. Isaac, you there?
I like just the ship show.
I'm here, yeah.
Eliezer Yehuda, you there?
Yeah.
Are you fascinated by this discussion? Would you like more jokes?
Sure.
I would appreciate more jokes.
There can never be too many jokes.
Okay. I thought you were going to say.
That's something that someone who's not heard too many jokes would say.
I thought you were going to say there haven't been any jokes up till now. So what do you mean more?
Ooh, that was a good one. We should have used that.
I kind of felt like
What'd you say?
nothing, unimportant.
Not important. It was a joke. Okay. So those are the preconditions, postconditions. Essentially, it's saying, think of it in terms of the case. The money is now lowered. You could say the precondition is you have to have money in your account to withdraw money. Kind of makes sense. But it's not necessarily true. Like I said, you could go into debt. Wait, I got to take a pill. Just hold on a second. I'll pause the recording. Okay, so that's the pre and post because I spent a lot of time on that. There's also the main flow. That's actually the main thing. The main flow is a list of the system interactions that take place under the most common scenario. For example, withdraw money, this would be enter card, enter PIN, etc. In other words, it should be numbered. It should, I would say like this, it should be numbered. You should number, it must be numbered. I'll say it like that. You must be numbered. 1, do this, 2, do this. Each step along the system, and maybe check. It could be ifs. If you entered this, well, but it's actually not going to have the ifs. The alternate flow is going to be the ifs, as you see beneath the main flow. In other words, the main flow is like what he would normally do. Enters this, enters that. But let's say he typed in the wrong card number. So it's going to say, if the card number is wrong, it's going to say, please re-enter. So that would be an alternate flow. It would be another way to get the information. For example, changing your password in Google. It asks you for your old password. If you don't remember your old password, then it asks you for your, confirmed email. If you don't have a confirmed email, then it asks you your mother's, your mother's father's first job. Whatever. Assuming you have a mother, your one of your parents, his parents' first job, if he had a parent and wasn't an orphan. So those are alternate flows, other ways to get to the same place. An alternate flow, well, possible alternative interactions. Exception flow, description of possible scenarios where unexpected or unpredicted events have taken place, which is actually, if you think about it, that's a contradiction in terms, because you're going to now you're now going to predict all the unpredicted things. That's impossible. If you predicted them, then they're right. If you expect the unexpected, then it's not unexpected anymore. It's expected. It's impossible to expect the unexpected. So what are the exception flows? Exception flow, this is my definition. This is what I've decided. I didn't actually see this written somewhere, but maybe you'll find it somewhere. What I think is the exception flows is in any flow which will cause me not to be able to take out the money. In other words, what's the difference between alternate flows and exception flows? Alternate flows are alternate ways to achieve the result, the desired result of the use case. Exception flows are flows that are sequences of events that will cause me not to succeed. Because if it's a recoverable exception, then it's really just an alternate flow. That's the way I understand it. But you could argue with that. But that's the way I understand it. I'm trying to make it very simple. Exception flows are flows that don't get there. You could argue that well, we'll see examples. We'll have to see an example. Fine. Questions? No, Daniel? Question?
Now I pretty much know UML diagrams from our class.
So then tell me, what do you think is the difference between exception flow and alternate flow? Am I right? Or you don't agree?
I don't think we covered that.
Oh, okay. So you don't know.
Yeah.
Okay. So now we have a case. Sales client, sales assistant, take order, customer. Okay. Sounds right. The sales, they both are using the take. In other words, we're showing both people who interact with the use case called take customer order. Both the sales client, the sales assistant who's going to help me take the order, and the customer who's actually going to get the order. So here we go. The main flow. Here we're skipping the short description. The main flow, actor enters customer details. It's a strange thing to say actor, but because they're two actors. But it means the sales, well,
And the customer isn't the one interacting with the system. It's the actor in this case.
yeah, but they're both called the actors. Or didn't we say that we didn't have anything else? There's nothing else that's other than an actor. These are all actors, no? We said way up here, actor. By the way, this example is different. Who's missing here is like the secretary. But an actor is those are all actors. So actor is a little bit imprecise because it doesn't say which actor. Of course, the truth is we usually say, I think I told you this last time, that the actor who is the source of the data is the actor who we're referring to. So really the customer is entering the data, even if he doesn't touch the screen, right? Well, let's think it's not the customer. Let's think it's the client. That's a straightforward way of thinking about it is that the worker, I mean, that's the way it works in the store, is that the worker enters the customer detail. The worker enters the code for the product required. The system displays the product details. The worker enters the quantity. The worker enters the payment details. The system saves the customer order. And it's not really a great example because there's, right, I mean, you see that there could be exceptions along the way. I could put in 6 things, but there aren't 6 things, in the store. The quantity could be rejected, maybe. You're not allowed to buy more than 2. Each of these stages could have exceptions. Alternate flow. After step 4, when the actor enters the quantity required, repeat steps 2 and 4 for additional products, because now he put in the quantity. Before I go right to payment details, I may go back to 2, put another item, pants and shirts he wants. Repeat 2 and 4, 2 to 4 as many times as you need. Resume at step 5 to enter payment details. So you see the numbering is important because otherwise I can't describe it in the alternate flow where the alternate flow begins. And it also means that I can leave out, I don't have to describe in the alternate flow from the beginning. I can just say the part that I want to describe. Okay. We didn't do this, take the short description. Now we're going to get to 2 more symbols. Now it's getting a little bit more complicated. Include and extend. So they're called stereotypes. Does anyone know why it's called a stereotype? David, if you know UML. In UML, anything that is in these inside of double arrows is called a stereotype. What is a stereotype? Yes.
A stereotype would be like that all stewardesses are female.
Right. That would be a stereotype. I thought a stereotype is like Bose is a stereotype or Denon is a stereotype. Different, like Sony is a stereotype. But I hear you. That all females are stewardesses is a stereotype. But tell that to my female cat. She doesn't think she's a stewardess. Extend and include. So there's a special meaning of stereotype in UML. I don't quite remember it, but so now we're going to talk about include. So You see, it starts getting complicated from this little picture of a circle. Now it becomes two circles, because what we're going to say is that this means it includes this. That means that B is always used by A. A includes B. A always uses B. Part of the procedure of A includes B. For example, this B could be like search for products on the system. And in that system, maybe it says enter the number of it, enter the color of it, enter the size. And then it tells you, no, we don't have any shirts that are that color and that size of this model. That's search for the thing. Now, it could be that every time I put in an item number, it searches the system because it needs to update that the inventory, right? When you sell a shirt in your store, you have to decrement your inventory of that item so that I can know what's in my store. And if something gets stolen, when I do at the end of the month, I do a product count and I go through all the items in my store and I see how many I got of everything. And I see what the system tells me I should have. And I know that somebody stole, a shirt of this color and this type. I also know that I need to order more shirts so that more people can steal them. So the search for the item may always be included in every sale. If this is a sale, the search for the item is included, but it's a separate system because I may use it in other cases. I may use it for certain cases of managing the store, or I want to see what, if I need to order more things. When I'm the manager and I'm ordering more things, I may also search for items in the store. So this is a separate case because it may be useful for various use cases. And just like I don't want in my code, in my C++ code or my Java code, I don't want to have the same operation, the same functionality written twice. I don't want the same use case written twice. So therefore, I'm going to separate it into a separate use case. Furthermore, now, okay, fine. So that's called include. So here they have an example of two cases. You see, I don't like that they have sale assistant here. I would prefer. See, here they have client. It's a little bit confusing. People who do this UML, even the people who, unless you're really getting into the deep authors, the main people who try to explain it a lot of times make mistakes. And I think this should really be the client, because he's taking the order. The client is giving the information. All the information is flowing from the client. I mean, actually, it's a little bit confusing. It's actually flowing from both of them. It's really flowing from both of them because, like, his name is going to be from the client, but the item details might be from the sales system. In any case, take customer order, return faulty good. So that's two different things that the system is going to do. It allows me to do that as a client or a sales system. But I could write it like this. He didn't do search. I did a search. Here's an example of identify customer. Whether I'm returning a faulty good or I'm taking customer order, I'm going to include identify customer. I'm going to figure out which customer is this that's returning. And what does it say? So, right, if you notice before we had actor enters customer details. So that's going to go for either of these cases. But, and then we're going to search for the customer. We'll Notice both of these will have that stage, and whatever the detail, if we change the way you identify customers, or if there's a lot of procedures in it, because you can identify it by his phone number, by his Teudat Zahut number, by his credit card number, by his name, by his first name, by his last name, by his address. There might be lots of ways to figuring, if you can't remember his, his credit card number, but he can remember his address, maybe that'll work. So you can identify customers lots of ways. All that'll be written here. And then I won't have to rewrite it for these two ones. So it's included. Now, if there would be a line, can anybody guess? What would a line mean? Notice that there's an arrow in this line. There's no arrow in this line. Because this arrowless line without an arrow means that he's doing this. This is that it's including. Now, also you'll notice that he drew it with a straight line here, and before he drew it with a dotted line. That can be confusing.
One's extending, one's implementing.
Well, we'll see. No, by the way, you always write the stereotype here, so you'll know what it is. But we'll see the difference between extended. What would it mean if there was a straight line with no arrow to here? What would the difference in that system be? Somebody explain to me the difference between the two systems, the way it's drawn here, and if I had drawn a straight line here. How would the system be different?
Would that be valid?
Yes, it would be valid. I'm giving you a thought-provoking question. Somebody, prove to me that you're out there.
Means that it's not a
We're out here.
stereotype and it's just it's a new concept to identify a customer. It's like a new concept.
Concept would change that word. I don't like the word concept.
A new
Input.
No, anybody else? Better word? Well, I'll ask you a better question. Is identify, I'll help you along. Is identify a customer a use case?
No,
Why not?
because it's included from take customer order, or take customer order includes it, I guess.
Right, it's not its own activity. What if I had a line here?
And it would be a use case.
Then it would be a use case. Then you could log into the system and just identify customers all day long if you wanted to. You could just, somebody walks into the shop and says, hi, I was wondering, do I have an account here or not? So you say, well, give me a shirt, and then I'll be able to take your order and find out if you exist. That would be the way the system is written now. But if he could actually say, oh, no, don't take a shirt, just give me your ID and I'll tell you if you exist in our system. Then identify customer would be its own use case, its own way to use the system. So that's what the line would mean there. It would mean that it is its own use case. This way, even though it's a use case in the sense that it's in an ellipse or an oval, you know why eggs are not shaped in ellipses, but ovals?
It's structurally superior to a circle.
No, that's a good guess, but no. Any other guesses?
Wouldn't fit out of a chicken.
No, it would fit out easier. So the
Wait,
answer,
what's the
both of
question?
your questions are the opposite. This is stronger than an oval, and this is easier to get out of a chicken than an oval. So why don't eggs
so they
have
don't
that shape?
roll off. They don't roll off high edges.
Right. If you roll an egg, it rolls in a circle. It doesn't roll in a line. That's so that they don't fall out of the nest or fall out of wherever they're. I mean, you could actually show that proves that originally birds didn't make nests, and they laid their eggs on the ground, and they just rolled them in circles and they pushed them together. You know what I mean? Because once you have a nest, it doesn't really matter with high edges. That proves that birds used to lay their eggs on the ground, and they didn't fly, and they actually were dinosaurs. Did you know that birds used to be dinosaurs in their youth?
No, chickens used to be T-Rexes.
What's the difference between the line and the arrow in the end?
Well, it would take more ink if you drew a line here. What does it mean in the
No,
diagram?
Yeah.
It means that there would be an independent use case called identify customers. In other words, you could use the system to identify customers independently of taking orders and returning goods. If it would, the way it's drawn now,
The arrow
Why
means
don't
it's dependent on the previous thing it's coming from.
now the only way to identify a customer is to pretend he's making an order and say, you want to know if you exist in my system, hand me that shirt over there, and I'll type in the information on the shirt, and I'll type in and then I'll be able to search for you, and it'll tell me if you exist or not. Because that's the only way I can do it, or by returning a faulty item. But I can't just do the action of identify customer on its own because there's no line. There's no interaction directly to this use case.
No. But I'm saying, how come from a sales assistant to take customer order, there's a line and not an arrow, and from take customer order to
Because that's the
identify-
way use cases are. Use cases, when you use a case, you put a line. When in one case includes another case, you put an arrow. Is that good, Yitzchak?
Yeah. Thank you.
Now, when I said a line directly, it was not a dafka line and not an arrow. You would never, it would be a mistake to have an arrow to here. That'd be a great test question of a mistake. Is this a mistake? What is the mistake in this diagram? Okay. Shimush simun. Okay, so include. So here's an example of doing an include. Well, you need to have two. Look here. Over here, actor records customer details. Include identify customer. And then the rest of the use case stays the same. And this include doesn't have to be in red, but it has to be written there, and you have to mention the name of the other use case in some way. You could actually, right. So now we can go, now that tells me, oh, jump to this other diagram over here and use this, identify customer. And it tells me the main flow. Actor enters search criteria. Could be the phone number, could be ID number, whatever it is, surname and postcode, zip code. System displays matching customer. And right, actor selects customer. Maybe it shows there's multiple matches. It could be that I type in the letter D and it shows me all of the users that have the letter D in their name. So then you select the one you want. Then the system displays the customer details just to make sure. Now it showed me that I chose DDD. And then I see his details. And then I see, oh, that's the right one. And I confirm, yes, I want that one. We can even have an alternate flow and identify customers. When you can't find the right customer, now we can make the customer. You don't exist in the system. Let's make you right now. And you add in his details and you hit enter and you're back to there. You have them again now. Notice it says resume at step 5, which is this step 5. So this description has no reference to who's using it. It's just describing itself. But in the one that uses it, that includes it, we are going to have to mention it. So we're getting like inheritance, So, right, we would just explain what we said already. Here it says, Tachbira hora'ah include eino kavua. It's not a fixed way of doing things with this include. But you should in some way, well, I don't know why it says eino kavua. I don't know what that means. It is kavua, you have to do that. But you have to also emphasize that you're including something, so it should stand out like you did in red or in bold or something. I wouldn't do it in red though. I would not do it in red. Okay. Now we have extend. Extend. I'm just wondering if you see, look, it's also drawn with a straight line here. But notice the difference. You see, how can I tell which is which? Really, the arrow is in the opposite direction. He extends, but also you should write the stereotype. But if you don't, I can still tell, because includes always pointing to the one that it includes, whereas extends is pointing the other direction. So let's go back. What does it mean? What does extends mean? A sometimes uses B. A mishtamesh b'nisibot mesuyamot. In certain cases, certain circumstances, A is used by B. Now, A mishtamesh B is used by A. Sorry, B is used by A. We have an example. Here, sell customer specific product. When I take a order, sometimes he says, I want this shirt, but I want you to print on it my name. So then I got to do other things. I got to get his name. I got to ask him what font he wants it written in. I got to do other things, but those I wouldn't normally do. And he just says, buy a shirt. So these are all, they're not always happening. They're sometimes happening. So if you think about it, that's why the arrow points the other way around, because when you do this one, you always do this one, right? When you sell the customer specific, you do this. So it's an extension of this, but it includes this. So that's why the arrow points towards it. Just like this one always uses this one always uses this one. So if you think about it, it's actually the same symbol because it's the same action, the same description. It's describing the same thing. When I sell a customer specific shirt, I got to do all the steps that are here. I can't just take his name and the font of the letters he wants. I got to also do everything here, his credit card number and everything. So this always uses this, but this doesn't always use that. It sometimes uses that. It's like identify customer. Sometimes uses take customer order. Sometimes it uses this. Sometimes it uses neither. If it had a line. In this case, it always uses either that or that. But you don't usually think about it from the backwards perspective. He uses this. And he sometimes uses this customer specific actions. So you can say that B improves or adds details to A in certain circumstances, for certain circumstances. If there's a line, then as we said, it means that he could actually do B independently. It means that he could do B by itself. He could do A by itself. He could do A and sometimes do B with it. Could he do B and not do A? According to what I explained, though, if he does B by itself, then he'll have to do A with it. So according to what I'm saying, logically, this doesn't really make much sense because, well, I mean, actually, no, we did exactly that case. We did here, this is a search, and this is buying a customer. But, you know, if you think about it, the search, in a sense, is expanded by the fact that you can also buy an item, which is how you get there. Anyway, a little bit too much philosophy there. We understood this example. So here, identify customer, which is always done. Here is sell, it's an extension. Fine, we understand that, I hope.
I feel like the arrow for extending should be going the other way. No,
Well, that's what I just
but
spent.
what's the lot? I don't understand why the arrow goes towards the more generalized thing.
Because you're right. It's hard to because if it would go the other way, because think about it as inheritance. This means inheritance. He is inheriting. How do you draw inheritance? If you look at this guy, I am inheriting from him, which means that when you do this one, you always do this one. But it doesn't mean when you do this one, you always do this one. This is
Right. Okay.
so that means that this one could be done without this one. So that means it's extend. It's only sometimes does it. So but when you do this one, you can't buy a customer specific item without also taking an order. So, but you could do this without that. So therefore, and here you can't do this without identify item, without identify customer. You must do this. So this, you must deal, this is kind of, if you think about it, this is kind of like a purely virtual class, because you can't directly do him. You must use something that inherits from him, that extends him. Whereas this, you can do either one. So this is this is not a virtual parent instance, right? You know, you understand what I'm referring to, yeah?
Yeah.
That's from your course on C++ or whatever. This would be a virtual, and this, or purely virtual, and this would be not. If I drew a line here, then this would no longer be purely virtual. It would, right? Okay. So he says that sell customer specific item is going to be its own use case. Well, that's kind of obvious. Anything that's in a circle is its own explanation. So here's sell. Let's look at how we're going to do it. So extend. So extend tells us that we are doing some basic use case. Right, but in certain circumstances, we're going to do the extend. So wait, well, I don't know, that explanation here in Hebrew didn't really add much. Let's look at the example. Use case, sell customer specific item. Fine. We don't have the short description of the main flow. After step 3, notice here, you see, when we wrote, let's notice the difference. When we wrote the this one, this is what? Identify customer. This was the thing we included. We have no reference to anybody else. We're identifying customer. And then in the one that's the one that we included. That's the added one. But the one that includes him is going to have to reference him, obviously. So here it's sort of the opposite. Because the arrow is pointing the other way. Here, after step 3 of what? After step 3 of what? So, well, we know that this one is only Let's go back. This is only after take customer order. So it must mean of take customer order. Only after step 3 of take customer order, because this one is, dependent on who it inherits from. And it's after step 3 of the one that I am extending, or see the way the word extending? I am expanding it. I'm adding more details to it, which means I'm a child, I'm an inheritance to it. After step 3, when the system displays the product details, if the product requires customer-specific features, actor enters customer-specific requirements such as size and color, and like I said, numbers, or a name that you want to print. And then resume at step 4. In between step 3 and step 4, we're going to do this step. You enter quantity required until step 6, where customer order is saved. At this step, the additional customer-specific product details must also be saved. So we see we have 2 changes. We have to remember to save also the details of this new thing, not just the normal customer order, but the additional things. Okay, let's take a break for 5 minutes.
Should we make the break longer?
How many more slides do I have? When do we finish?
5?
Yeah, we can make the break longer. We can make the break for 10 minutes. Okay.
I'll pause the recording.
Yeah, Paul. So now we're on to activity diagrams. Everybody can hear me all right?
Yeah.
Yep.
Yeah. Okay. So activity diagrams, they describe activity. So you can use them either in software or in business for describing business activities. You have operations, actions that happen. I guess activity here he says that activity diagrams can be used to describe what happens between several use cases. But in any case, it's a dynamic diagram. And a dynamic diagram means that it shows behavior. Dynamic means it moves as opposed to static. So this is the classic one that you've learned is, class diagrams. They're very static. They don't show you what the order of operations is. So activities should try to show you some kind of seder, some kind of progression. It's like a flow chart. I don't know if you guys learned flow. Did anybody learn flow charts?
Yeah.
I learned flow charts before they let us program, way back when I was in high school. Let's see some examples. The Hebrew slides tend to describe everything before they show it to you. I like to sort of show it to you, then go back and describe it. So here are a bunch of symbols that you can use in them. And you see that these are similar to flowcharts, if you know flowcharts. Well, who does not know flowcharts?
Most of the people here.
So flowcharts are really, the most basic thing and most important thing in programming like I said, I learned it in high school. Maybe you do know, you just don't know the name. Here, this looks like a nice one. Is it going to show me? Not quite big enough. Can you guys see that? It's also not a perfect flowchart, but it's so small, jeepers. Wait, let me go back. I can't read it.
Do we have to make a flow chart for computer architecture?
You're not going to have to, but I still want to show it to you. Because it is relevant. Now, what if I go like, oh, actually, you know, I like this one better. Okay, yeah, this is a good one. Here's a nice one. Never mind. That other one didn't like. This one I like. Start. It always starts with this. Usually it's a circle instead of a, this is like a capsula, like a pill. But you have a circle that says start and a circle that says end or stop or finish. And then what you do is you say, like, declare variables A, B, and C. Every box is a action, a process. And then they use, like, I guess, slanted boxes. You don't have to. You could also use a box. I generally just use another box. But here they did, like, slanted boxes for input. Read A, B, C. So first you declare them, then you read them. Then you have a question. Is A greater than B? If it is, go this way. True. And you write true and false on these lines here. Is A greater than B? If it is, then is A greater than C? If it is, then A is the biggest number. Print A. This is like an input or output. This is like an internal process. So, and then you're done. You printed A. Now, if A is not greater, if A is not greater than B, then is B greater than C? Now, we've already determined that B was greater or equal to A. So now is B greater than C? If it is, then print B. If it's not, then print C. So also here, if it's not, print C. So you have now determined of the three numbers, which is the greatest, and you've printed it on the screen. This you've done in a flow chart without knowing C++ or Java or any language. Now it's just to, now it's a small thing to just translate this into whatever language you want. But you notice this is not language specific, and it's describing an algorithm, right? So we use flowcharts to describe algorithms. And this is really the way, anytime you have an algorithm, you should solve it like this before you start programming. Just because it's, you don't get bothered by having to think about how do I do that, in this language. You just first solve the problem in a mathematical way. This is like a mathematical way. So that's a flowchart. So we're going to see that the things that we're doing here are the same. Here, initial node, that's your start. That's your stop. Decision node is your triangle, just like it was in the flowchart. Here, they do a capsula for an action or activity. It means a process. And this is a flow. So far, the symbols are exactly the same. It's pretty much exactly the same. But you see, it shows activity. Just in that one we did with the greater than or less than, it was showing you the sequence. It matters the order. If you can't do this if you didn't first declare the variables and take them in from the user. So the order is important. So it shows you the flow. That's why it's called a flow chart. But here we're calling an activity diagram. So they just made it a little bit more complicated, but it's the same thing. This is so funny. See, I am taking from him, but he took from somewhere else and then just put the Hebrew. He took from a certain website. I'm pretty sure I know which one. A certain website that shows you UML, and he changed it into Hebrew. So now we have to rechange it back into English. Managing of, manage worker. And then we have a question. Does the worker, you don't have to write anything in here because you're going to write the question, the solution. Instead of true and false, we're going to write the worker exists, the worker does not exist. If the worker exists, then the worker, did he stop? Did he quit? Did he retire? Has the worker stopped working? Or is he still a worker? If he's still a worker, because remember, in databases, like I told you before, you never delete anybody. Essentially, we're asking, is he an active worker or not? Because once you're a worker in our company, you're always in our database. Because we may have an audit for the IRS, for taxes so anyway, is he still a worker? Yes. So change whatever information you want to on the worker. And then come to this triangle here. Now, if you notice in the flow chart, the arrows could just merge and come right down to here if you wanted. That's what it had in the other one. We saw that there were two ways to get to printing C, and they just merged. But here you have to put a diamond. You can't merge without putting a diamond, even though this diamond actually has no question that it's asking, because you can't merge arrows without a diamond. So the worker has been updated. Now here, what we're saying is, if he's a new worker, then create a registration, create an entry in a database for him with all the information that you want, and then go here. I mean, this is very simple flow, but it's just showing you. You see, it's more like a business flow, or it's a corporate flow. Flow in a business. It's not like just dealing with numbers and letters like we dealt with in the flow chart. I mean, of course, this is a flow. Essentially, this is a flow chart also, just drawn a little bit differently. Now, here is a activity diagram for chat. A chat session. You want to chat. So what do? First, you log into the system. Then you either send or receive. After you send, you can either, let's say you first send. So then you can receive, and then you can send and receive and send and receive and send and receive. But you can also send and then send again, and then send again and send again. And you can also receive and receive and receive again. And also, after you send it or receive, you could always log out, and then you're finished. Okay. We're giving you very simple examples. You're gonna have to translate these into your chosen system. Right? You're gonna do this for your whatever system, whatever information system you're doing in your lab. So here is a system for managing orders. So the customer sends an order request. That's a process. You see, there's no check, there is no decision making here. Order request system confirms the receipt of the order. Okay, he tells them your order is received. Check if the order is a normal order. If it is a normal order, then confirm the order and dispatch the order, and we're done. If it's not a normal order, then check if the order is a special order. Oh, here, by the way, he did it the other way, where he wrote yes and no, and he wrote as a comment here. There's different ways of doing it. Check if the order is a special order. If it is a special order, then you also have to confirm the order and go. But if it's a normal order and it's not a special order, then you're finished. And notice you can have 2 termination points. That's also true in a flow chart. Basically, this is a flow chart. Not really much difference in a flow chart in this, except that it's capsules instead of rectangles, and it's and we'll see. There's still going to be some more development. Also, you don't write anything in this triangle, and you have to have 2. And the arrows have to, if they come together, they have to come together at a triangle. Okay. Now you can also have a fork where this you didn't usually do in a flowchart. I mean, you basically, I mean, you could have, I think, but you never actually did this. But here we're doing this. You can have parallel actions. What this means is state A and state B occur at the same time after state 1. Then you have to have like 2 CPUs. Two states are simultaneously occurring. So let's see an example of that. Turn on the TV, choose a TV station, then you watch and listen to the voices. You analyze the images and analyze the voices. Then you turn off the TV. Maybe some software that's analyzing TV or your brain could be described in this way. In other words, this state is a repetitive state. Listen to, I mean, you could also draw like an arrow to here again, you know, different ways of thinking about how to draw it. But you can also, once you have parallel, you can also join together. And here, this looks like a line, just like this line, but it's actually a special line. It's a thicker line, and it allows arrows to join together. In other words, don't think of it as flowing, as this flowing and then coming here, because then we would need a triangle. What it's saying is, this hits a bar, and this hits a bar. When they reach the bar, then when they both reach the bar, then it continues to state F. In other words, we'll only go to state F when state A and B are finished. They bang into this bar here. And this only when this bar is full of all the arrows that hit it, will it go on. So enter departure and arrival dates, enter personal info, search availability. You have to do both of these things before you go to select flight. If there's no availability and there's first you got to put the dates, and then you got to check availability, and you got to search personal information. Now, you can't continue to here without having done these ones. And we won't go to this state until these two. So you can say, well, why did you just put one before the other? Why did I draw it like this? Why not just say first search and then check this? So what's the answer? Can anybody tell me? Why? My question is, what is the difference between writing it like this and writing one after the other?
Because then one would have to wait for the other, but now they're concurrent. So.
Right, one would have to wait for the other, exactly. Or I could even say it like this. We're not requiring that they are on 2 different CPUs. But we're saying that as far as the system, it doesn't matter which one happens first. It's an ignore. You know, like you have a 0 or 1 or an X. This is we don't care if one happens before the other or the other happens before the one. But right, it also could be if we have multiple CPUs, we could use multiple CPUs. But the point is, it's not a requirement that it's in parallel. The point is that we're saying we're not requiring the order to be in a specific order. That's really what we're saying. Now select the flight, select flight, enter points, hotel reservations, enter points, hotel reservations. So select flights. I don't know what reward points. Does he have reward points? If no, then go to get the payment information. If he does have reward points, yes, then enter the points, enter the reservation. In other words, the system you'll ask you, do you want to use points? And then he says yes. And then it'll go into a section where it checks how many points he has. And we'll say you have a maximum of 50. Do you want to use all 50? Or you want to use only half of them? And then it'll do that. So you have a choice here. And either way, we're going to get the payment. So what we saw there is we have a fork, which is this one, and a join, which is this one, this bar. So that's also something that doesn't really exist in a flowchart. So it's kind of like an advanced flowchart. Although obviously you can see that, you could just add that to the flowcharts and then it would be a flowchart. Now you can do one more thing with these things, make them a little bit even more complicated. And you can say, we can define the behaviors as being related to particular classes, of functionality. Classes of functionality. Remember, a class can have many functions in it. So what class will be doing the different jobs? So here we're doing a different example now of ordering a car and, ordering repairs. Sorry, repairing a car. Or actually not repairing a car. Maybe it is. No, I think it's more like renting a car. So the lakua, you have a function in the class called lakua, called client, which is order a car. And what he does is he orders a car, which means like a function is supposed to do something to the client, it's supposed to do to itself. So he orders a car, he associates to himself a certain car. I don't know, Kabbalah, the reception desk. It actually executes the order, and then the lab, not the lab, the garage, it actually brings the car. I mean, it's a little bit of a stupid example. It makes sense in the physical world. I'm trying to think about it in programming. Programming, this doesn't really make sense. Like bringing the car, what would that be in programming? Registering the car to him. And then this is still part of the garage. Charge the customer. And we also have to order the car. And in other words, these functionalities that are in parallel, because I don't care the order, but they're being done by different classes, whether it's the garage or the reception desk or the client himself. I don't like this example so much because I don't know what the client is doing, why that's an action to himself. But anyway, pay the bill, and that's something that the client does. And then the garage or the Kabbalah, I'm not sure where this is actually anymore. It's in between. Should be right under this. Closes the husband. So the point I'm trying to show here is what we have is like swimming lanes. Imagine a vertical line here and a vertical line here. And we're saying like you're swimming in your own lane in an Olympic-sized pool. So we're not only showing you the flow, but we're showing you who is responsible, which section of your program is responsible for doing these processes. Where do these processes, where is the functionality of these processes written? In which class? So that's called swim lanes. That's it for lecture 4. Let's start lecture 5. Any questions on that?
Nah.
When do we finish today?
5 o'clock.
Do you think we could maybe have a review class like in the middle of the semester or something? Because I mean, we're going to be, if we continue at this pace, we're going to be pretty far ahead. I mean, or no class, but
well, we're not going to have a review class. I don't see the point. If I'm recording everything and posting it, you can review yourself. But we'll see. The later part of the course, it might take longer. So that was 4. Where's 5? Oh, here's 5. You guys are just so smart, that we go very fast. Okay. So here I'm back to my slides. Class diagrams and sequence diagrams. So here we're getting some more diagrams. And that's the end of I think it's the end of the diagram section. Then we're going to go on to more theoretical stuff. I mean, this is also theoretical. but it's theoretical with practical application. Practical, you can draw diagrams. So this stuff is this is going to be review for you. Class diagrams. The purpose is to show the relationship. Here I did translate it. The purpose is to show the relationship between the various classes, which classes contain, use, or create other classes, and to show inheritance. So the basic representation of a class is like this. The name of the class, usually a smaller box, and then attributes and methods. What are attributes and methods? Who remembers? No, Daniel.
Yeah. What's an attribute? I don't know. It's data. Yeah.
Attributes are data. What's methods?
Methods are things of filling data or doing stuff. I don't know. Functions. There.
Functions. Thank you. What we used to call functions, this is now 20 years ago or 30 years ago was decided is a bad name. Bad. Don't call it functions. By the way, in Pascal, it was called it's called procedures, I think. Now then it became functions, and now function is a very smart name because it's like a mathematical function. It has the result. But now we call it methods because we don't want to call it a function because we're not interested. There's no results. There should be no return values. The principle of object-oriented programming, one of the many principles, is that no functions have return values. And they only, if they have return value, it's just success or failure. But really, they have no return values. The other theory of functions is they have no parameters. Right? You guys agree with me?
What, that functions have no parameters?
Yeah, well, not all functions, but the
It's-
ideal function has no parameters and no return value. It just behaves. It's a behavior of the class itself to itself. All the data that it needs should be in the attributes. Why should it have parameters? Except for like the constructor function. But basically, why should it have attributes? It should, why should it have parameters? Anything it needs should be in its attributes, which it has access to.
What if it's a class that acts by definition on other classes?
Then it has a pointer to that other object in its
No, but like in
attributes.
general, like you have some sort of class that represents something, and then you give it another instance of itself, and then it works out its relationship with that one. For example, like.
You mean like a linked list where you're adding another object of the same type?
Yeah, sure.
So
every object in the world should be already known by the linked list, so that when you tell it to add, it knows already which object to add. It makes no sense.
Well, like I said, there are constructor functions that have parameters. If you're constructing the linked list, so you may have to give it a object.
Yeah, but what if you want to add them later on based on, I don't know, conditionals or anything else?
Yeah, I guess adding they're right. The most basic way I'm thinking about it, but the most obvious way to add something to a linked list is to have an add. Well, what would you do? You'd have an add function in your linked list, and you'd have to point to which one you're adding. And the linked list can't possibly know which one to add unless you give it as a parameter. So yeah, there I would say you're right. I'm just saying the ideal function would be like if you would do as you would have a class called math, and it would have in it two digits, two numbers, and then you could do either add on the numbers, subtract on the numbers. And when you construct an object of this type, obviously you'll supply the two numbers that it's going to work on. But then once you've constructed the object called math, it now has a behavior called add or subtract or multiply or divide. And those functions don't take any parameters. If I want to add two new numbers, I'll just create a new object called another object of type math. And when I create it, I will give it the values that I want to give it. And then I will run the function add on it. You see what I'm saying?
No math library ever does that.
Right. Well, because in math, you don't do that.
It
For
would use a
simple
lot of memory,
things,
no?
but then it's not object oriented. I'm just saying, if it doesn't do it that way, then it's just saying that object oriented is not ideal in all circumstances. But if it would be, if you would be brainwashed into being Mr. Object Oriented, then that would be how you would do a math, and it would work.
No, a calculator is still object oriented. There's like the object that like makes the calculation.
No, I don't agree. Just because you have objects doesn't mean you're object oriented. I mean, I don't know how exactly you didn't describe your program very detailed, but just having by the way, you're not allowed to remain in the class unless you have a background, which is this alien spaceship or I just want to point that out to those people that have failed so far to put a proper background. But it wouldn't be, what are you saying? Yeah, just because I use an object and then it doesn't mean I'm really programming in object-oriented programming. Object-oriented programming is a way of thinking. It's a new way of thinking. It's a way of thinking where everything is an object that behaves on itself. So if I make them, I don't know what I don't know what exactly your example was. What was your example? Oh, now everybody's just doing backgrounds. You had a question? Wait, you asked me something, no? Somebody asked me something and I was answering it. Anyway, that's object-oriented. Fine. Example. Here's my example. Note, values assigned at construction are listed after equal sign. Return, in other words, this is like a default. In other words, we're giving it an initial value here. Return types of methods are listed after the method parameters and inside of brackets. So for example, compute GPA is, you see, by the way, look at my nice example. You see, it's a student and he has a function. He can compute his own GPA. He returns a float. How does he compute his GPA? Well, he has a list. I'm so smart. I mean, not so smart. Sorry. I like this example. See, I made this example, so therefore I like it. Everybody, Adam la'atzmo karov. I made a list of grades. He has a pointer to a list of grades. He has it. I'm not giving him any parameters. He has it. He has a list of grades in himself. Obviously those grades are independent objects, but I have a list of them. And when I want to compute my GPA, I take that list and I go through it and I compute it. Now I can also have a function called set name, which obviously will take a parameter. And that is of type string afterwards and the new name. So anyway, the way you do it is you type the name of the parameter and then afterward the type. Name is the name and the type is string. ID is the name and the type is integer. And the name of this class is student, capitalized. Now, why do you do it this? Notice that the names are capitalized. The attributes are capitalized, and because why are they capitalized? Because they're classes, really. Everything here is really a class. Grades is a class. I mean, it's an instance of a class of type list. Set and compute are always verbs. The methods are verbs, and they're always lowercase and then capitalize the first letters of each word. Set name, right, it does take a parameter because I got to set the name. If I got to get it at some point, I have to have input. You see, this is a nice class because he can do things to himself. He can set his own name. He can compute his own GPA. Questions?
None.
None. Okay. Visibility. We also need to list the visibility of members, attributes, and methods. For example, they can be public, private, or protected. Plus symbol means public, the minus is private, and the pound symbol is protected. You all remember what those things are. If you don't, you can ask me. We list the appropriate symbol before the member name. For example, name is going to be private. You can only change it with the public plus set name function. Right? You can't directly access the string name. You can only use it through set name. Why would I do something like that? Can anybody explain to me why I made it?
What's the question?
Question is, why would I do something like have the name be private and then have a set name be a public function? Why do I want to prevent you from directly accessing this name?
So we can like check if it has weird symbols in it and stuff.
Right. Exactly. We can check that if your gender is male, you have a male name, for example. Not allow you to have a female name. Or if your gender is non-conforming to standard definitions, then your name will also be non-conforming to standard definitions of names. Whatever rules we want to impose on our names, we can do that through set name. Must be pronounceable, for example. Class relationships. Classes relate to each other in various ways. Dependency is when one class uses another class in some way. There are two examples where we have simple dependency. Now we're getting to stuff that you did not probably learn. Did you learn about dependencies? Anyway, we're getting very philosophic here. Ronnie, you learned something?
No, sorry.
No, I appreciate having human interactions. I mean, if you are human, I don't really know. Like, you could have been replaced.
I'm actually a spaceship.
What?
I'm actually a spaceship.
You're a spaceship. Are you an object-oriented spaceship?
That doesn't take any parameters.
No parameters in your spaceship. Okay, there are two examples where we have a simple dependency. Class A has at least one method with at least one parameter of type B. Now, this is going to be questions on your exam, so you're going to have to learn this. Because I just, I spent a lot of time explaining this in the past and clarifying it. Class A has at least one method with at least one parameter of type B. Class A instantiates at least one object of type B in at least one method. In both cases, A is dependent on B. If the definition of B is removed from the source code, A will break. And if B's behavior changes, A might break also. So again, class A has at least one method with at least one parameter of type B. So for example, I have a function called set name. If string all of a sudden changes, I'm dependent on string. If string all of a sudden only accepts ampersands, pounds, and dollar signs, then my function will not work anymore. If string changes, I'm dependent on it. I have a method that accepts as a parameter. Furthermore, I have one object of type B, but notice I instantiated it. I instantiated an object of type B in a method. So that you cannot see that in this picture. I don't know what is in compute GPA. By the way, not having an object here is not that. I didn't say having a attribute, which is, well, I mean, I would say you could almost say call chicane, even more so if it has an attribute. Well, we'll see. No, if again, if I have set name, if in here I have a parameter that is a type string, then I'm dependent on string. If compute GPA has inside of it, I don't see it though, but inside of compute GPA, it has a object of type, I don't know, float verification. I don't know, float verifier, float truncator. If that object of type float truncator changes, then my compute GPA won't work anymore. So that's a dependency. How to draw dependencies. So like I said, since the parameters I drew here, so maybe that I would know, but here I wouldn't know that he uses float, what was it called? Float validator, I don't know. If I wanted to show that he uses this class float validator, I would say that my student uses class float, is dependent on float validator. That's dependency. As to be
Dependency is different than inheritance.
Yes. Notice the dotted line. It's not inheritance.
I assume a solid line will mean inheritance then.
Yeah. Yes. Solid line will mean inheritance. It's not inheritance at all because I didn't inherit from string. My student doesn't inherit from string. He's not a string with extra functionality. He uses a string. He needs a string to do his stuff. His function has a string in it. That's a dependency. Association. Association is used to describe a tighter connection between two classes. A tighter connection, a stronger connection. Association is usually bidirectional, but it can be unidirectional, in which case it is called a navigation. So navigation is unidirectional, but you could call them both associations. Unidirectional. What is a unidirectional association? Again, this is stronger. I didn't, remember we talked about the Three Amigos? So they invented all of this, or they defined how to name it and how to draw it. I don't like the fact this is called dependency and the next one is called association, because to me, dependency sounds stronger than association. But association is actually stronger than dependency. Now there's a stronger relationship. Class A has a pointer of an object of type B. Class A is a pointer to an object of type B. So that means, for example, I don't know whether grades is a pointer or not. I don't know, but maybe it is. Maybe grades is a pointer. So then I have a pointer to something of type list. So I'm associated with lists. I have a pointer to it. Again, if list changes, it'll break something on me. But it's a stronger one. Why? That's a good question. Why? But class A has a pointer to an object of type class B. Bidirectional, class A has a pointer type B and B has a pointer type A. I use him and he uses me. That would be a bidirectional association. How to draw unidirectional. Unidirectional association is with a solid line and an arrow. You want to see inheritance? Inheritance is drawn with an open arrow end and a line.
So what's the difference between inheritance and association?
Well, we didn't get to inheritance yet, so.
Not inheritance, I meant whatever the other one was, dependency.
Again, dependency is where a function has it, either as a parameter or an object declared in the function.
Oh, but if it's
But if it's not a function, if it's an attribute that is a pointer to another class, like list might be a pointer to an object of type list somewhere else. There may be some list out there that grades is just a pointer to it. So that would be a stronger connection, because my attribute itself is actually another class, is actually another instance of something out there. Not just if the code changes. See why it's worse? Oh, now I got a good answer for you. It's not just that if the code changes, but if the thing itself gets deleted, I'm lost. I have a pointer to nothing. In other words, it's actually an object that I'm using. I'm not just having my own version, my own object of your type. It's much more likely that the object will get deleted than that the type will get deleted. So it's a stronger association than dependency. So we draw bidirectional like this. One unidirectional. Sorry. This is dependency, the weaker line. This is association, a stronger line. The significance of the solid line is that there's a tighter or stronger connection here than there is in mere dependency. This is because the class has an attribute, an actual attribute of the type of the other class, not just a method with a local object, not just a method with a local object of the other type. And my attribute itself, not just my methods, have it. And we draw bidirectional the same way, but without the arrow. A contains a handle to B. Here, B also contains a handle to A. They each have a pointer to each other. Now that we've explained that association is a stronger thing than dependency because it's in the actual attributes and not in the functions or methods, now we can talk about two different types of association. And these are rather well known: aggregation and composition. Aggregation, okay. In our example of association, A had a pointer to an object of type class B. Right. We had a point, like we had a list. Our list pointed to an object. Our grades pointed to an object of type list. We had a pointer to an object of type B, type list. We did not discuss who constructed this B. That's the interesting question. Who made the B? In my constructor function, I could have created a list of all the grades that my student is going to have. And it starts off with an empty list, and I keep adding to it. I constructed it. What's the other alternative? Can somebody tell me what the alternative is?
What if the class itself builds it?
Well, you still have to say who created the class. What class it's in. In other words, every class gets created by some other class. Right? No classes are just appear. Your main class could create a bunch of classes or something if you want in the beginning. And not a lot of times when you wrote a program in data structures, you probably wrote your main. Your main looks like something like this. My list equals new list, and then you gave it 0 or something. And then my student equals my, equal you at the beginning, and their main had like 4 lines, and in those, and that's all your main was. And it was just creating a few instances. Does that ring a bell?
Yeah.
So I said that there's 2 ways that student could create a list. That's the way I said. Student could create a list of grades, and he created the instance. What's the other alternative? Or what's another alternative? It can't create itself. Even God didn't create himself.
It was passed in as a parameter. or something.
Are you maybe referring to the builder like design pattern that you can have like a larger class build it, or is that the first? I think it seems like it's the first.
Well, forget I don't know about the design patterns. I'm not talking about that. I'm saying that name me the class. If I have imagine a system where I have students and grades, and it's a Moodle system or something, or it's a student management system. Either every time I create a new student, the student creates his own grade list, or some other class creates the grade list. Who are good candidates? What other classes might you have in your system to create a list of grades for a given student? Well, the system itself could, right? I mean, theoretically, the system, you could have a system class that it creates for every time it creates it. The system class is going to create the student, isn't it? I mean, somebody has to create the student. So the system class will create that. The student management system will create that. And he could also create a list of grades for the student, theoretically possible. I mean, that's
and then it's passed into the student object.
And then exactly. And then when the student is constructed, I pass a pointer to that list that I created, that the system created. And the system creates the student. What?
So the list will actually get destroyed if the original class gets.
So then the list is independent of the student. If the student, well, you're thinking in Java about how the garbage collector works?
Yeah.
I'm not thinking about Java. Imagine there is no garbage collector. So when if the student would somehow get destroyed, the list could go on existing because maybe somebody else is using it. Maybe the teacher has a pointer to that same list,
Yeah, but what if the management system gets destructed, but student?
Well, the management system gets destructed, then the whole system is gone. That's the system. We're not going to worry about that.
Okay, whatever. What if another class?
Yeah, then just because the constructor of a certain object gets destroyed doesn't mean the object is destroyed. Even in Java. In Java, the way it works is if I have if A creates some list and then passes a pointer to B, and now B has a pointer to the list, and A also has a pointer to the list. Even if A is destroyed, B goes on. B still has a pointer to the list, so the list will still exist. The garbage collector detects when there are no longer any pointers to the list, then it deletes the list. So it doesn't matter who created it. It matters if there's still a pointer. But
the slide says that it's independent of the lifetime of A.
Right. So what it becomes, wait, I didn't get there yet, but so if A creates the list and B has a pointer to it also. So there's two people potentially pointing to it. The question is, when which one of them is destroyed, does the list get destroyed? Now, in Java, you can't know, but in C++, you could know because you have to explicitly delete something. Now, it's normal practice to have the person who created the object and his destructor to also delete all of the things that he points to. That's normal procedure, but it doesn't have to be that way. If you have if you have like a factory pattern where your whole goal is to create things to give out to other objects to point to, then just because your factory disappears doesn't mean that you don't maintain those pointers necessarily. You sever your tie to the thing you created, and now the other guy has a pointer to it, and it's his job when he gets deleted to delete the thing that he's pointing to. You follow?
Yeah.
So that's the question. Who is responsible for deleting the thing? Am I going over you guys' heads, or you guys all know all of this, or is this new? Or you're understanding what I'm saying and you're
Well, I took a class on this.
What?
We had a similar class that talked about this.
Which class was that?
Functional, there's advanced object programming and fundamentals in programming.
By who? Who taught that?
Shachar Golan did the advanced object orienting and
Ariel Stallman.
yeah, Stallman, Ariel Stallman.
Yeah, but only the third years here took it. The second years here haven't taken either of those yet.
Ariel Stillman, he's my chavruta. Or used to be my chavruta. He's my chavruta from 20 years ago. Yeah, excellent teacher, Ariel. The other guy I don't know. But yeah, these are concepts that you should be familiar with. I obviously don't have to spend so much time on it now, but anyway, it's interesting. It's nice to talk about. I think that's why Ariel has this class on it. It's interesting to talk about. The question I always have that I never got a good answer for is, give me a case where it's done wrong and the system doesn't work right. Like, you know what I mean? Like, if I did association instead of aggregation, if I did aggregation instead of composition, or composition instead of aggregation, when is my system going to go haywire because I did it wrong? I want an example of like the wrong, of how it matters.
Well, when you're deleting stuff, it depends when you're deleting stuff.
Yeah, but if you do everything right, I can make a dog that is aggregate of legs and tails and heads. But I can also make it as a composition of heads and tails and legs. And I can make it work. I can make it work either way.
What if you have an aggregation and composition of a file with a file system? If I delete the root, do I want to delete everything that's inside of it? Or if I delete it, I want to leave whatever's inside of it?
Okay, you're saying it's just a choice that the system designer has to make.
No, whatever. No, we're talking, the whole thing is from all this stuff is part of class diagrams. It's how it's not, the system is implemented however the person that programmed it.
Yeah, but how should the designer decide? Well, anyway, that's what I'm saying.
System. Let him
but you're the designer. We're the designers now.
Well, the software, whoever's paying the money, follow the money.
You're the designer now. We are designers, software architects. We are the world, as Michael Jackson said. You know that song? Yeah.
Of course I know it.
I don't know.
You don't know it?
I remember when it came. I remember when it was new. So it was so long ago. I thought that, I don't know if it became part of the canon of known songs. Okay. So Yitz, are you following?
I'm here. I don't know if I would say following, but I'm here.
What'd you say?
Yeah, I'm here.
You're here. Are you following? I asked.
That's debatable.
All right. I knew what I was saying. So at least somebody here knew. They say that is in Kabbalah, they talk about Razin de Razin, the secrets of secrets. And they say that, like, I heard this from I think Moshe Idel. I don't remember exactly what he's referring to, but he says the first stage is that there's just that the speaker is speaking secrets and the listeners don't understand. The second stage is that the speaker is speaking secrets, but he doesn't understand exactly what he's saying, but the listeners understand. And the third stage is the speaker is speaking secrets that he doesn't understand, and the listeners are listening and they don't understand. Nobody understands what they're talking about. It's like his example was, what about if you have, like, I ask, what is the meaning of the word meaning? You start getting very lost.
That phrase, which of the three states do you think he was in?
Moshe Idel, Professor Moshe Idel. He was he himself. I think that he was saying that I don't know. Sorry, I think maybe it was different. Maybe I don't remember exactly what he said. It's a long time ago. Maybe he said that. I think he was saying that he didn't understand. I think he did not understand what he was talking about, but he knew he didn't understand what he was talking about. That's a different point. You can not know. You can think you know and not know. If the object of class B was constructed by class A, then we call this aggregation. See, we're talking about who's constructing it. Aggregation means, see, they always give the example. Aggregation is, a bedroom. A bedroom has a bed and a dresser and
Just go with the
and-
folder example. If you delete the main folder, it deletes everything else inside of it. As ownership of all the.
that's a good example. I have to say, is that Ariel's example?
No, that was Shachar.
That is an
Ariel taught us the.
That's an
what's-
excellent example. I like that example. That's a very good example. But before we get to that example, I want to give a less good example, which is a room can be aggregate. A classic example: a room is an aggregate of a bed, bedroom, a dresser, a wardrobe, a sink, maybe. But and all these things are independent objects that exist outside. They are not constructed by the room. You could have a room with nothing in it, and you could remove these things, and the room would still be there. But the room is really an aggregation of all those things. You need to have those things in the room, but those things. Sorry, I said it wrong. You need to have those things in the room. If you don't have those things, it's not a room anymore. But those things could exist outside of a room. You could have a bed in the factory, or a bed you could have a bed in the living room. You could have a dresser in the living room. But when you aggregate those things together, then you formed a room. As opposed to a composition, which is like the classic example of composition is a human being. The human being is a composition of an arm and a brain, let's say a brain and a heart and legs. And without those things, he's not really a human being anymore. Or maybe not, human being is not the best word, but like a functioning Homo sapien is not functioning without legs and hearts, and he's not properly functioning if he doesn't have those. I mean, I don't want to, people who are without legs and arms may still be human beings, but I'm just saying they're not fully functional human beings. But there's no meaning to a leg existing outside of the human being. We have no interest in collecting legs and arms, and they have no other use except to be connected to human beings, unless you're Jeffrey Dahmer. But basically, they have no other uses. So a human being is a composition of those things. So what does that mean? That means that when I make a human being, really, I should construct the human being class should be in charge of constructing the legs and the arms. When I construct a human being, automatically his class should construct his parts. So what I don't like about the first example with the room is that, like, yeah, but you could kind of imagine a leg outside of a room, and you could imagine a bed outside of a room. So what's the difference? And you could imagine a room that when you made it, you constructed when you make the room, you make the beds and all those things for it. So you could. But what they're saying is, if it's aggregation, what you're saying is the person who is responsible for constructing the class that was responsible for constructing the bed was not the class that was not the room class. But when you're talking about composition, the human class is responsible for constructing. He actually constructs and also deletes. When you delete the human being, there'll be a loop, or not a loop, but there'll be a series of commands where inside the destructor, you'll destruct all the things that he created, the legs and the arms and things. But when you delete the room, you won't necessarily destruct the bed and the things, because maybe those beds are useful somewhere else. That's the idea of aggregation and composition. Now, Daniel said a great example, which is that a folder. The folder class should construct, if you want to add a new file to the construct, then the class should construct. It's actually not the greatest example, but because I'll tell you why in a minute. But but it's also a good example because you put, when you create you don't create the files when you create the folder, but when you do create the folder, who's doing it is the folder. When you do create a new file, the folder is creating it. And therefore, when the folder gets deleted, you'll also run a delete on all the things. So a folder would be a class. So yes, which is a folder an example of? A aggregation or composition?
Composition.
Exactly. The only problem I have with it is, well, yeah, okay, fine. You could have a folder that has a file from another folder being moved into that folder. So then all of a sudden the new folder becomes responsible for deleting it, even though you didn't create it. So it's actually more than the construction, which I wrote here. It's the deletion. Maybe I should change that, but was constructed and will be deleted by A. So the importance of class A not having constructed class B is that the lifetime, and here's a key word, the lifetime of B is independent of the lifetime of A. If A is destroyed, B can go on living. Their lifetimes are not interlocked. But in composition, since A constructed B, when A is destroyed, B will be destroyed. That's the normal. See, normally it goes together. When you construct something, you're also in charge of deleting it. That's a general rule that you would have followed in data structures. Whenever you created, whichever class was the class that created it, he'll be the class that deletes it. But of course, it doesn't have to be that way. Like I said, if you're like a factory type situation. In truth, B could be constructed by A and not be destroyed, like I just said, if another class points to B. In Java, it
So it
won't be
doesn't
destroyed.
really matter who created it.
Right. In that case, the relationship would be called aggregation. Because just because I destroyed it, it's still around, so therefore it must be aggregation. The ultimate determinant in whether we have aggregation or composition is whether the lifetimes of the objects are independent or dependent. So even though it's in parentheses and in smaller text than anything else, that's the last sentence here is the most important thing here. Is that clear to everybody? Questions? Not clear to somebody? Is that not clear to somebody, but they don't want to talk about it anymore anyway? Okay. I assume that means that you all want to talk about it more. No, just kidding. Diagramming association, aggregation, composition. So it's a little bit misleading because association is really includes aggregation and composition. So association is really, if you think about it, right, two kinds of association are aggregation and composition. So if you think about it, association is really just a not yet fully defined type of connection. In other words, we're not specifying who created who deletes who. We're not specifying the lifetime. But in aggregation and composition, we are. So here's how you draw them. You draw a straight line without an arrow, and you draw this diamond here. And if the diamond is filled in, it's a stronger connection, so it's composition. If it's not so filled in, then it's merely aggregation. And this means that A is an aggregate of B and perhaps other things. In other words, this means that A has in it a B, but if you delete A, but A is not in charge. In his delete function, he does not delete B. That's what it means, actually, in the most technical sense. His delete function does not delete B. Example of composition. So here you go. That's the classic example. Person, brain, heart, legs. When you delete person, you presumably are going to delete all these other things. They're also going to disappear. You don't need those things. Of course, this is a dumb example because, you know, you don't program people. Like a file, you do kind of program. Better example. Now we have multiplicity indicators. Wait, do we go until 5?
Yeah.
So let's stop here. Oh, let's stop here. Let's take another break for.
Any chance we could just stay in this link instead of switching to the other link?
There's nobody in the other class that's not in this class?
No.
Okay, so yeah, we can do that. So let's just stop the recording.